So, welcome back and let us continue our study of first order logic. We have defined the syntax, we have defined the set of sentences, we have defined the semantics in the sense of interpretation as to what do sentences mean, and we said that you give us some set of sentences and what they mean will depend upon what is the domain that you are talking about. And we saw this example in the previous session, where we said that the same knowledge base could mean different things if you are talking about different domains essentially. Let us now come to truth assignment, because we want to be able to decide as to when is a sentence true. Remember that formulas in general may or may not be true, because they may have free variables, but sentences are formulas without free variables, and therefore, they will have to be either true or false essentially. So, how do we do this? And let us do this first, then we will move on to theorem proving. So, like in propositional logic, we are now trying to define a valuation function. Now, we are calling it val, like Shakespeare said, a rose by any other name is just as sweet. It does not matter what the name is essentially. So, we are defining this valuation function val, which will take the set of formulas and map them to this two valued set, which is true or false for us essentially. So, essentially we want to say which formulas are true, which formulas are false essentially. How do we define that? We start with the simplest sentences, the atomic sentences. Top is always true by definition, bottom is going to be always false by definition. An atomic formula of the kind T1 equal to T2. Remember, that is an atomic formula. T1 and T2 are terms, equal to is the equality sign in our logic, and we are saying is this formula true or not, but to decide that we have to say you give me an interpretation mapping and you give me an assignment function, and then I will tell you whether the formula is true or not. And the way to decide whether this formula T1 equal to T2 is true or not under the interpretation I and the mapping A is if and only if the two terms under the same mappings, mapping and assignment, they map to the same element. So, they are the same. See, by the time we have done this thing, we have transported from a formula or this T1 and T2 are terms, we have transported from terms in the language, which are just symbol structures, to elements of the domain essentially. So, if there is some domain D, we say that this maps onto some element under this I and A, depends on whether it has variables, whether it has constants, and whatever the case may be. Interpretation and functions. Interpretation will tell us functions and constants, assignment will tell us where A maps to, where variables map to, whatever it is. So, we are taking care of both interpretation and assignment, and we are saying this term maps to this element and this term also maps to this element. That is what we mean by equal, that they map to the same element. If they map to the same element, then our original formula is true. Okay, so, we have figured out how to give truth value to this one kind of atomic formula. The second atomic formula we had was that if Q was a predicate name and T1 up to Tn were terms, in first order logic the arguments to predicates are always terms. We will see perhaps that can we kind of be more expressive than that, can we allow something more, we will think about that later. As far as we are concerned, in first order logic the arguments to predicates are terms, and so a formula, an atomic formula of the kind which says a predicate name Q in this case, which takes n terms as argument, we want to find out whether it is true or not. So, you say first you tell us what is the interpretation and what is the assignment, and then we will say that yes, that formula is true if and only if once we map the terms onto the individual elements in the domain and we create a tuple out of them, then we will just check whether the tuple belongs to the image of the relation, the predicate essentially. That image is a relation and the relation is a subset of n d cross d cross d, if you remember essentially. So, essentially an atomic formula which uses the predicate symbol is true if it corresponds to a tuple which is present in the domain essentially. So, here are some examples here. We say color lily equal to white is true. So, before we do that, you must figure out, we have not yet come at a convention as to how we will distinguish function names from predicate names. One way to do it is to use capitalize names for predicate names and lowercase names for function names. So, that is of course, a syntactic way of doing that. But even without that, you should realize that this is an atomic formula which uses equality, which means the input to this formula, which are the two terms T 1 and T 2, they must be terms essentially, which means color lily is a term, which means color is a function essentially. So, it is a function which takes anything and maps onto something called a color essentially. So, lily is pink or lily is white or rose is red or whatever the case may be, that it takes something and as an input and maps onto a color essentially. The color is also, we are assuming, is an element in the domain essentially. So, we have a domain, for example, like this, in which is a subset of a larger domain, in which we have let us say white and black and red and so on. So, let us say a simplistic approach to colors is that there are colors in the domain, and white of course, will map to what we have called white in the domain. By now, we have got used to that idea, and let us say color lily also maps to white essentially, which is to this. So, if that is the case, just like we said here, if they both map to the same element in the domain, then we say that the formula is true. So, color lily is a color, which means in the domain it must be some color. White is also a color, which means in the domain, in the subset of colors, it must be a color, and this formula will be true if both of them map to the same color, which of course, as far as we are concerned, is going to be white. But it is a mapping, somebody might, if they want to pull your leg, they will map white onto blue, and then you would be wondering why is this lily blue, but that is a different matter. So, if they both refer to the same color, then that formula is true. So, in a similar fashion, the president of USA and the commander of the US Army, the commander in chief maybe of the US Army, is true if again they refer to the same person essentially. Of course, in this case the person is not even identified, at any given point it is identified. So, currently for example, the president of USA is Biden. So, this president USA will map to Biden and commander US Army also will map to Biden, in which case this sentence is true. If less than is a predicate, then less than 5 7 is true if this tuple that we make out of 5 and 7 belongs to the less than relation. So, we are assuming that this less than relation is a long table in which there are two columns, and the first column number should be smaller than the second column number essentially. So, 5 and 17 must be there in some row. If you think of it as a relational database, then as long as this tuple belongs to that relation, then we say that sentence, it is an atomic sentence. It is a sentence because it has no free variables. We do not need quantifiers to make sentences. We need quantifiers only if we have variables. So, this sentence less than 517 is true, provided this pair of 5 and 17 is, let us just say, in our understanding of what it means to say that something is less than that. That understanding could have been an explicit table essentially of everything that is less than everything else. Of course, we do not do construct such tables, that is why maths is more interesting, but that is the principle behind it. In a similar fashion, if I say the sentence brothers Suresh Ramesh is true, so here I have skipped out the mapping part. Remember that Suresh under the interpretation and of course, Suresh is a constant. So, only under A I should have written that A here essentially, but anyway. So, I hope that does not cause any confusion. Likewise, this brother is under the mapping I, that is what we said here, right, that the relation name or the predicate name in the mapping I gives you a relation in the domain. So, we are assuming that the same names carry forward. So, that does not cause any confusion. So, for formulas with connectives, logical connectives, it is the same thing that we did in first propositional logic. So, it is exactly the same. So, if a formula is true, then a negation of that formula is false, and so on and so forth. One more example, we can see that if alpha is true and beta is false, then alpha implies beta is false. In any other case, it is true essentially. So, that is a short way of describing the truth table for alpha for implies essentially. So, we can define the truth assignment essentially using the truth table essentially. Now, we come to quantified formulas. So, a formula of the form there exists alpha, there exists x alpha such that alpha is true if there is some value of x for which the formula alpha becomes true essentially. In a similar fashion, a universally quantified formula for all x alpha, which says for all x this formula alpha must be true, is true if it is true for any x that you choose essentially. That is the meaning of for all men are mortal means you give me any man and that man will turn out to be mortal. Formally, we can define it as follows. So, remember this x is a variable essentially. Of course, it is a quantified variable, but what variables are subject to assignments essentially. So, we say that an assignment B, what is an assignment? Assignment gives values to variables. We say it is an x variant of an assignment A if these two assignments, which are functions from variables to elements in the domain. We say it is an x variant if they map all variables to identical elements except for this variable called x. So, that is why we say it is an x variant essentially. So, if they agree on all variables except x. So, we use this notation and then we say that a formula like there exists x alpha is true. Whenever a formula is true, we have to say okay, we are specifying the mapping and we are specifying the assignment is true essentially. We say that such a formula is true if there is another mapping B which is an x variant of A and it is true for that mapping essentially. In other words, the formula alpha is true for some value of x essentially. So, if I say there exists x even x, and if I am talking about natural numbers, then it is true because I can produce a natural number, say 6, and say that 6 is even. So, therefore, it is true that this formula is true. In a similar fashion, a universally quantified formula is true if, see, in existentially formulas we said for some assignment, in universal formulas we say for all assignments, that any x variant you take, this formula must be true. Why x variant? Because x is a quantifying variable, x is being quantified for all x or there exists x. So, you take any x variant of whatever assignment that we are talking about A, take any B. So, you can change x to whatever you want and the formula must be true, and that is the intuitive meaning of for all x, that you take any value of x and the formula will be true. So, finally, to the set of sentences. So, remember that a set of sentences, a sentence in FOL is a formula without any free variables. This means that all variables in the formula are quantified essentially. As a consequence of this, and you should think about this a little bit, that the sentences are true or false independent of the assignment mapping essentially. So, when we said that there exists x even x, we said this formula is true for natural numbers, this formula is true if the domain is natural numbers. It does not depend on the assignment essentially, it is independent of the assignment mapping. You do not have to give me some specific this thing. This formula is true. Why is it true? Because by definition it says that there exists some x variant, which means there exists some value of x, there exists some assignment in which this formula will be true, and that is why this formula is true and we do not need the assignment function. That is why we work with sentences in first order logic. We do not work with sentences like even x. That is a formula, but it is not a sentence because it has got a free variables. We cannot determine the truth value of such a statement, such a formula. Okay, so, we have said that the meaning of terms and sentences of a FOL is given by the interpretation, which means you choose a domain and you choose a mapping as to what do the predicates mean, what do the functions mean, what do the constants mean or refer to. We say that an interpretation M, so you have chosen some D, you have chosen some I of a set of sentences. Sometimes people use the term theory for a set of sentences. So, this kind of thing, language and physics people talk essentially. So, we have this theory of gravity, and then which is basically a set of equations and sentences, and then they say, okay, is there a model for this theory or something. So, can we verify experimentally whether the theory has a model or not. In exactly the same sense, we say that a set of sentences which we will call as a theory in the language that we have chosen, an interpretation M is a model if all the sentences in the set are true in that interpretation. So, at the surface level, when you read this, it is similar to what we said in propositional logic. We said that an interpretation, in which case that was an assignment, is a model if all the sentences in our knowledge base become true essentially. We are saying something similar here, is that an interpretation is a model if all the sentences in our knowledge base become true, except that here we are talking about all this mapping between the language and the predicate symbols and function symbols and so on. So, we are choosing a domain and we are choosing an mapping, and that is an interpretation. So, whatever domain and mapping that we choose, if that makes the set of sentences true, then we say it is a model essentially. And these terms that we had seen earlier, tautologies, satisfiable and unsatisfiable formulas. Also have definitions here. A tautology is a formula of the language that is true in all interpretations essentially, which means, see, in proposition, I am kind of repeating this a little bit. In proposition logic, when you said all interpretations, it means all valuations essentially. So, we said that you give me a formula like P implies Q implies P, and we said it is a tautology because you give me any value of P and any value of Q, and this formula will evaluate you true essentially. What we are saying in first order logic is you give us any model, any interpretation, you give us any domain and you give us any mapping, and this formula will be true. So, it is true in all interpretations, which means any D, any I, you choose this thing and this formula will be true. And of course, there are simple formulas like this. I am sure when we read it as saying that Suresh is happy or Suresh is not happy. So, we have an image of people essentially, but it does not matter whether the domain is talking about people, whether the domain is talking about numbers, whether the domain is talking about plants. It does not matter what is the meaning of happy essentially. You choose a domain, you choose an interpretation, and this sentence in our language will be true irrespective of what interpretation you choose, what domain and what interpretation you choose. Always true, a sentence which is always true. Sometimes we also call this that it is a valid formula. So, a formula is satisfiable if it is true in at least one interpretation. For example, all men are human essentially. If my meaning of man was, let us say, our standard meaning of man, which is human, or let us say a person, and if my meaning of human was let us say inanimate or dead or something like that, then to say that all persons are dead would not be a true statement, right. So, in that interpretation it would not be true, but what we are saying here is that you can choose some domain and some interpretation in which this formula will become true, and then of course, in the domain and interpretation you would have chosen some appropriate meaning for man and for human essentially. There are no constants in this and there are no functions, but you can choose an interpretation which will make this true, which is which is true in our world, that all of us are humans essentially. Human is different from humane. Finally, formula is unsatisfiable or a contradiction if it is true in no interpretation. Anything that any interpretation you choose, any meaning of happy you choose, any meaning of mapping of Suresh you choose to individuals, you can never make this formula true essentially. So, what is more important is that when we create a knowledge base which has sentences, which has quantifiers and things like that, and then we say, does this knowledge base have a model? What it means is that you can create a domain and an interpretation in which that knowledge base will become true, and we are interested in that model, and then everything that we are talking about pertains to that model. We are less often interested in tautologies and unsatisfiable formulas in the first order context essentially. So, now we have got a good idea of first order logic. We looked at the syntax, we looked at rules of inference, we looked at semantics, how a meaning is given by an interpretation. We also looked at truth functional semantics as to how one decides whether sentences are true or not essentially. So, like we have been doing, we will move to proofs after this, and we will see how proofs can be found in first order logic. We already seen that we introduced two new rules of inference which are specific to first order logic. One was the universal instantiation rule, which says that for all x p x, then p must be true for some specific individual, and generalization, which says that p is true for some specific individual, it must be true for some there exists some x t x. And we saw a couple of rules of substitution, De Morgan's law, pushing the not inside quantifiers and things like that. All that machinery is available with us now, and we want to see that if given a knowledge base and given a query, can we now prove that that sentence is true? If it is true, means can we build a complete logic that if it is entailed, then we can prove it essentially, and we want to look at some algorithms for proof essentially, but we will do that in the next video. So, see you then.